Alright, so I'm getting everything prepared to get the class started today. So if you have any questions, now is a good time to ask, right before class. Um, and we'll get the class started in another minute or two. The YouTube site should also it's also up and running already. So we have both Discord and YouTube up and running at this point. All right, I'm not seeing any questions. So let me lock the preview again, just so that I don't accidentally change anything in OBS. Alright, we got 20 seconds before we start today's class. I hope you guys all got a chance to read the rest of the Aleph No module, because it's actually kind of interesting. I mean, to me, it's interesting. Okay, maybe not to you, but to me, the section that talks about the two-dimensional space, folding into one-dimensional space, that was kind of interesting because I found resources that talks about how to fold the space, but nobody actually provided an equation to actually write the function itself. So it's only a concept, where I did the research, and I basically finished it up with a closed equation. Alright, so it's time to get started. It is 12 o'clock, it's noon time. So what we'll do is we are going to fast forward in module 0293 to the portion, to the part that we kind of stopped talking, and we'll get through it today. So we'll go ahead and get to section 5. Okay, so section 5 is well, let's go back to section 4 first, okay, because there's a term that is kind of useful. So the cardinality of n, the set of all natural number, is infinite, but it is also called countable. There are sets where the cardinality is not countable. The set of all the real numbers, for instance, is not countable. So that's kind of how we define infinitely countable sets. And the set of all natural number is. So anything that has the same cardinality as the set of all natural numbers is also called infinitely countable. So on Monday we took a look at integers, right? So because the integer number line extends on both sides infinitely, so we would normally not think about that as something that has the same cardinality as the set of all natural numbers. But because we found a bijective function to map between the set of all natural numbers and the set of all the integers, that is the piece that we need to basically say that these two sets actually have the same cardinality, which is Aleph null. Alright, so which part is what is complicated? What is it referring to? I'm referring to the text channel message. The function itself or the concept? The concept, that two sets, has a bijective function established between them. Alright, so I'm not seeing any clarification to the comment in the text channel, so I can't really act on it, because if it is just a general comment, the derivation of what? of the function that we'll be talking about today, or the function that we derived the other day. Function f, that maps between the set of all the integers and the set of natural numbers. Alright, so I'm suspecting Darwood is using YouTube because of the lag time. So there's a reason why we want to be using Discord whenever it's possible. Alright, so instead of waiting, I am going to start with section 5. So section 5 talks about a two-dimensional space. Oh, the function that we are going to talk about. Okay, so that's not surprising. Okay, that's actually pretty normal that people find that one, or function g, which is the function that we're going to talk about, to be a little bit, I wouldn't say confusing, but there's a lot of parts, okay, to kind of put it together. So what we'll do is we're going to use the tablet, okay, so that I can give you a graphical representation of what we are doing. Okay, so here's the tablet. So what we're doing here is we are now looking at a two-dimensional space. So we got x going this way, we got y going this way. So this is not unusual, right? I mean, because in all of your other math classes, you have encountered two-dimensional spaces, except this one is pixelized. Okay, I use the term pixelized, just because there's no 1.5 or 1.25, in either of the axes. So the axes would start with 0, then it goes to 1, 2, 3, and so on. And we've got 1, 0, 1, 2, 3, and so on. So the x-axis is the set of all the natural numbers, and then the y-axis is also the set of all the natural numbers. So the question is, okay, I look at all the coordinates, okay, so we have 0, 0, which is this coordinate over here. We have 1, 1, which is the coordinate over here, and then we have 0, 1, which is the coordinate over here, and then we have 1, 0, which is the coordinate over here, and so on. Okay, so now the question is, so we are looking at the Cartesian, we're looking at the Cartesian product of natural number and natural number itself when we're looking at these particular elements. That is the domain that we are talking about. So now the question is, what exactly is the cardinality of the Cartesian product between natural numbers and natural numbers? That is the question. Okay, that's the question that we want to answer. And hopefully by the end of today's lecture, we'll see that, hey, this really is the same thing as the cardinality of just natural numbers, which is kind of surprising, right? Because we can sort of see how integers can be folded into natural numbers because they're single-dimensional, to begin with. So we just have to kind of interleave, things a little bit, then they seem to fold out, just fine. But when we are talking about a two-dimensional space, that seems to be just kind of interesting, right? I mean, just intriguing that you can fold a two-dimensional space into a single-dimensional space, which is just a number line. So that's what we're going to talk about today. So the general idea of doing this mapping is really easy. Okay, so let me remove all of these pixels. So the way we do this is we simply number the pixels sequentially, but we sweep in a diagonal way. So I'll just go ahead and do it a few diagonal lines. So this is numbered, it has a sequential number of 0. This has 1, this has 2, this one is 3, 4, 5, 6, 7, 8, 9, and so on. In other words, we are basically just using diagonal lines to, okay, if I were to draw another picture, so we're just going like this, this, and so on, in order to assign a single natural number to a quote-unquote pixel in that space. So if you want to see it in a pixel way, all you have to do is to actually complete the grid lines, then you can see the actual pixels. I suppose I can change the background to be graph paper kind, but not all of the lines will show up, unfortunately, because this is a shrunk screen from what I actually use, and because the lines are kind of thin, so some of them would actually disappear, just like what you see right here. Okay, so it doesn't really kind of help if I use a graph paper background. So do we have any questions about the general idea of how we are assigning natural numbers to each pixel in a two-dimensional space? So let me just kind of pause and make sure that there are no questions at this point before we go any further. All right, you got a question coming. Cool. All right, so the question is, so the benefit of going diagonally is time complexity of the algorithm, or is it something else? It's just one way to do it, and because all I need is a way to map the pixels to natural numbers. And this turns out to be one of the many ways, potentially one of the many ways to do it. Okay, because what I really want to do is to see if this is actually an equality. Can I establish the equality between the cardinality of the Cartesian product of natural number with itself versus the cardinality of just natural number? That's what I want to establish. So what we are trying to do is to find a g as a function where it maps the Cartesian product of n times n to n. And we want this g to be bijective, because if I can find such a bijective g, then I can claim the equality up here. Alright, so that's our objective. Okay, the objective is to establish that equality of the cardinalities. The way to do it, the mechanical part, is really just what I have just demonstrated, which is to assign values in a diagonal way. So we just on each diagonal line we go from the lower right corner to the upper left corner, and then we move on to the next diagonal line, which is the one to its quote unquote right hand side. So we keep sweeping, those diagonal lines until we get to the square that we want to assign a natural number to. So are we good so far? Okay, does everybody understand the mechanism that we are doing, at least by hand? Okay, very good. So now we can say the g of, okay, I'm just using an example here. So if I look at this particular pixel over here, it has an x value of 1 and a y value of 1 as well. So now let's pick another one. Let's pick the 8. Okay, let's pick this one here because it has a different value for x and y. So this one has an x value of 1 and then a value of 2 for y. So it is at coordinate 1, 2. Okay, so 1, 2, which is an element coming from here. Once you apply the g value, it should return 8 in this case. Okay, obviously, if you look at the origin, which is 0, 0, it maps to 0, and so on. So the double parentheses in this case is not a typo; it is actually required. The outer pair of parentheses is for the function for the application of the function itself. So that's just the syntax of how we specify the parameter, or the argument in this case, of using a function. And then the inner parentheses are for specifying the two tuple, which is an element of n Cartesian product with n. So that's why double parentheses is actually needed here. We cannot simplify and just say, oh, we can remove one of the pairs of parentheses. They're both actually needed in this case. So now I want you to think about this. Okay, G of 123 and 69. No, I did not plan this. I just pulled some number out of thin air. But I want to find out what natural number would be on that particular pixel if we just kind of sweep diagonal lines and keep extending to the right hand side with our diagonal lines. So the answer is, well, Tech, do you really want us to do this? Because this might take a while. Some of you may say that, right? Some of you may say, well, maybe I can just write a program to do it. Okay, maybe it would be a double loop program where the outer loop would control which diagonal line, and then the inner loop would go through each diagonal line and then keep incrementing a counter until we get to the pixel, okay, that we want to find what the natural number is. So yes, we can do all that stuff. Okay, it is possible. It's possible to do it by hand. It is also possible to do it by using a double loop, logic. But the question is, do we want to do it that way? Well, if we can avoid, we would like to use closed form formula. Okay, which basically means we just have addition, subtraction, squares, square roots, division, and so on and so forth. Okay, so we don't want to use loops unless we really have to use loops. So that's kind of the derivation that we are going to go through today. They're all in the notes. Okay, everything is written in the notes already. So all I'm doing today is to give you a live demonstration of what is already presented in the notes, and also to give you pictures, because it's not really that easy to include pictures in the format that I use to type the notes. So I'm using a tablet to give you that presentation of using graphics in this case. All right, so shall we move on, or are there any further questions? All right, so it looks like there are no further questions. All right. So to figure out the closed form, okay, we have to find out, okay, what kind of observation is going to be helpful to us. So let me just erase a portion of what is on the screen because it is not really needed for this discussion. So I'm going to take that out, okay, cut it, okay. And now what we'll do, okay, I'll need to switch back to tool. Okay, there we go. So now what we want to do is to try to see if we can find some patterns, right? So can anyone tell what is going to be the value of this pixel here? Just guess, okay? Think of this as an IQ test. You are given the sequence 0, 1, 3, 6. What do you think is going to be the next one? 10, very good. And what about the next one? The next one being the one on this side. 15, and then 21, and so on. So you guys already figure out, hey, there's a pattern to it. Okay, we are not looking at a general pixel, but we are looking at pixels on row 0. Okay, everything that has y being 0. But there seems to be a pattern, right? Because 0 to 1 is adding just 1. 0 plus 1 is 1. And then from 1 to 3, we have to add 2. From 3 to 6, we have to add 3. From 6 to 10, we have to add 4. From 10 to 15, we have to add 5, and so on and so forth. So that is a pattern. But that pattern can be explained because when you fill in the diagonal lines like this, each successive diagonal line is going to have one more pixel. And that's why, when you look at the base of the diagonal lines, their values are increasing. The difference between their values is also incrementing by 1, for each adjacent pixel at the base of the entire thing. Are we doing okay so far? All right, cool. Oh, by the way, I found some shortcut keys that can be useful, in Discord. So I know this is a distraction, but it's kind of useful because we're using the Discord text channel for a lot of things. So if you type Control/ on the keyboard in Discord, okay, so make sure that you're in Discord, and then you do a Control/, it will pop up a keyboard combo, okay, and there are quite a few shortcut keys that you can apply to messages, which is the first part. But then the question is, how do you determine whether the focus is on the message or not? Okay, so I got to tell you guys this because I was very excited when I find this out, and you guys go like, but I have known this for years. Well, it's new to me, so that's why I'm excited. Alright, so this is the Discord window that we have for today's class. So what we can do is, the first thing is you have to quote unquote select a message. Oh, by the way, this is what it appears. Okay, what appears when I type Control/, and this is the description. Okay, it says these shortcuts work when focused on the message. So now the question is, how do we focus on the message? So the first thing we do is to press the Tab key, and that will focus the editing area to type a new message. Okay, so let's just say that I want to go back to Aiden's message and give it a OK hand. Okay, so we basically just kind of go back to here, and then the shortcut key to add a reaction is the plus key. So once I press the plus key, I can go through, I can basically type what emoticon I want to use. So I can say thumb up like that, and then press the enter key. So that makes it kind of easy-ish to do things. But there's another way to do this. Okay, I use a program called AutoKey, and I'm pretty sure you can find equivalent programs in Windows to do about the same thing. Let me get the Windows show up first. Okay, so this is AutoKey. It is a Linux kind of thing, so it's not going to be the same for Windows. But in Windows, you guys are gamers. Some of you are gamers, right? So you know everything about how to program keys, for macros and so on and so forth. Get one of those programs, okay? So the other thing now I can do is I'm associating an abbreviation, with adding an OK hand. So if I want to add an OK hand to Aiden's message, I can now just type plus OK, and it will automatically finish the rest because I programmed the macro to finish the spelling of OK underscore hand and then press the enter key. So all I need is to start it, which is plus OK, and I don't even have to press the enter key. It will auto finish the rest of it. So this is kind of cool, because not in this class, but in my CISP440 class during the lab time, I have lots and lots of messages to respond to, and some are basically just acknowledging, yes, I got your message, oh, I'm so glad that you got it figured out. So instead of typing, I usually just give it an OK hand to basically go like, yep, good job, stuff like that. And I just found this shortcut to be quite useful, especially when you use it in conjunction with something like AutoKey, where you can type a part of it and it can auto finish the rest of it. So, yes, I know this is a distraction, but I could not resist. It is just too cool to be ignored. Okay, so getting back to here. So what we want to do now is to say, hey, in general, okay, if I want to find the G value, okay, the natural number corresponding to a pixel, if I want to find something and I know that the Y value is a 0, which means it is on the bottom row like this, I know this is just going to be 0 plus 1 plus 2 plus blah 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 all the way up to x. So is that observation okay? I mean, just converting from how we figure out the values of the pixels at the bottom row, from that I generalize to something like this. So I want to make sure that this generalization is okay first before we proceed to say, okay, but this still needs a loop to evaluate. We'll handle that later. So are we good so far? I just want to get some confirmation before we move forward. Cool, cool. All right, excellent. From the responses on the text channel, you guys can also think about, adding like shortcut keys and macros and whatnot. So you don't have to type yes and then the enter key. You just kind of go to the Discord window, and then you just press, a hotkey combination, and then it will automatically pop up, your thumbs up or OK hand, whatever you want to use, to basically say yes, I'm okay to proceed at this point. Okay, all right. So now what we'll do is to say, what do we do with this? Okay, so this is basically a good time for me to kind of evaluate whether you guys really have taken CISP440 or 372 or not. Because in the pre-calc class, they probably have talked about something like this. So if I have a sigma notation where where I goes from 0 to x, and each item I'm going to sum is just I itself, there's a closed form to this already. Okay, this is not a big thing. Many classes would talk about this already. So if you already know what that should be, good for you, because you remember something from your pre-calc class. If you don't, it's okay too, because I actually derived this entire thing. So assuming that you did not take, or when you took CISP440 or 37, well, not CIS, sorry, math 370 or math 372, if they didn't talk about this, okay, if they didn't give you a closed form of this sigma or summation notation here, let's go ahead and do it ourselves. Okay, so if you refer back to my notes, I have this derivation here. Now you guys would go like, but Tag, it's not necessary to derive this, because we know that 0 plus 1 plus 2 all the way plus x really boils down to x times x plus 1, the whole thing divided by 2. But why, right? I mean, without the derivation in between, you're just taking the words of somebody else that, the summation of this sequence has a closed form like this. You'll be taking the words of somebody else. This is the actual proof. Okay, it is a very step-by-step proof, so that we can actually say, okay, the first thing we notice is, if the number of items we want to sum is even, it is we group it into one case. If it is odd, we group it into another case. But you can see that eventually they merge back into the same equation, which means, regardless of whether x is even or not, we use the same closed form to figure out this particular sigma formula. I think this is introduced when people are learning, when they are learning integration, switching from a sigma of discrete parts, under a curve, to the smooth curve itself. So they would basically divide that region by n, and then n approaches infinity, and then so your sigma notation eventually become the same as the actual integration formula. And that's kind of where this notation would come in handy. And this is also when they will start to talk about this sigma formula is basically the same as x times x plus 1 divided by 2. All right. So I'm not going to go through this proof here, but you are more than encouraged to take a look at the derivation and see if you can find out, what I use to go between the lines. Okay. It's really just math. Okay. This is really just algebra. The only trick that I use in this case is I try to unify the indexes. So you can see how, in here, I goes from 0 to x minus 1, the whole thing divided by 2. And then over here, I have I going from x minus 1 divided by 2 plus 1, and then all the way to x. So the trick is to combine these two sigma into one single, sigma, and changing the indexes so they share the same index. And the only thing I had to do is to change, instead of I here, I have x minus I. Then I would be able to modify the indexes. That's kind of the trick that I used multiple times when I went through this derivation. So so as I said, it would be nice if you have the time to actually figure out, how the derivation works. If you don't, it's probably okay, because I'm not gonna ask people to regurgitate, this derivation here. I mean, we're gonna have our exam online. It's gonna be open book and open notes. There's no point in testing knowledge. Okay, there's no point in asking people, do you know blah blah blah? Well, everybody can just look it up. So the exam is going to be focused on problem solving. All right. So given this, okay, so now we know. So let me switch back to the tablet first. Okay, so now we know that g of x0 is what we just saw earlier. It is x times x plus 1, the whole thing divided by 2. Well, that's pretty cool, right? I mean, at least we can solve the g value for the bottom row in the two-dimensional space. So getting back to the example here, we now know, okay, so if I were to use a graph here, and let's say this is 123. So we know that this pixel here, at the bottom here, this thing is going to have a g value. Okay, so this is the g value of 123.0 because it is at the bottom. And we know this is going to be 123 times 124, the whole thing divided by 2. Okay, that's kind of cool, right? And then somebody's going to say, but Tech, that's not what we are trying to figure out, because what we're trying to figure out, the one that has the y coordinate at 69. Ah, man, you're right. What are we going to do? What are we going to do? In fact, that the pixel that we want to figure out is kind of over here, where this is 69, right? I mean, what are we going to do? Well, as it turns out, there are some other things we can do. There are certain other things we can notice as well. So the other thing we notice is on every diagonal line, if you look at all the pixels in a diagonal line, and you add up the x and the y component of each pixel, they add up to be the same. Okay, so if this is not clear, we'll go ahead and take a look. So we start with coordinate 0, 0, and then we have 1, 0, and then here we have 0, 1, and then we have 2, 0, 1, 1, and then we have 0, 2, and then we have 3, 0, 2, 1, 1, 2, and then 0, 3, and so on. So if you focus on one single diagonal line, okay, let's just focus on this diagonal line here, okay, you would notice that 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, 0 plus 3 is also 3. Oh, okay. So that means, if you know the sum of the x and the y component of a particular pixel, you can find who is at the base of that diagonal line. Now, let me say that one more time. Okay, if you know the x and the y value of a particular pixel, like the one that we are talking about, okay, 123. Oops, I put a comma too soon. So we have 123 and what, 69, I think. Let me check. Yep, 69. All right. So we know it belongs to a diagonal line that is really far from the portion that we have already explored. But doesn't matter, okay? Because we know if you extend the diagonal line all the way down to the base is going to have the coordinate of the base is going to be 123 plus 69, which is 192, I believe, and a 0. So we know 192.0 is at the base of the diagonal line that 123.69 belongs to. Are we doing okay so far with this observation? Because the sum of x and y of all the pixels along a diagonal line add up to be the same. So is that okay? Okay, we got some people typing. That's good. All right, very good. And I'm going to wait for Jonathan. I'm sort of lost what we are trying to calculate exactly. We're trying to figure out the g value of 123.69 in this case. And the only thing we can figure out is the g value of everything along the base of the two-dimensional space. So we have to start somewhere, right? So we have to go back to the base of the diagonal line where 123.69 as a pixel belongs to. That's kind of the intermediate step that we are currently working on. Is that okay? So we want to find out the g value of this thing here, but we already know how to find the g value of this thing here. So now the question is, how do we go from the g value here all the way to the g value here? But that is really easy, because everything along the diagonal line is just plus 1, plus 1, plus 1, plus 1, blah blah blah, all the way to the pixel that we actually want. In other words, the y coordinate is how much we need to add to the g value of the base of the diagonal line. So that means, okay, in this particular case, it means the g value of 123.69 would be the g value of 192.0 plus the y value, which is just 69 itself. Are we doing okay so far with this? Which then turns out to be 123 times 120. Oops, okay, I take it back. I got myself confused, which is 192 times 193, the whole thing divided by 2, and then plus 69. That would be the natural number as a g value corresponding to the coordinate of 123.69. Alright, so I'm going to pause, okay, so that you guys have a chance to kind of catch up with what I have shown up to this point and see if we have any questions. Alright, I'm not seeing any questions, which I'm not really sure whether it's a good thing or a bad thing. Either everybody is getting it, or people don't even know how to ask questions. All right. So I'm gonna move forward, okay, without any questions. I cannot just wait indefinitely, right? So I'm gonna time out and I'm gonna move forward. So now the question is, oh, so this is a concrete example. From the concrete example, how do we generalize? So the generalization is g of xy is going to start with the value of g of x0, because that one is pretty easy to get to, and then we just have to add y to it. Oh, I take it back, not x. It's x plus y 0, because that is at the base of the diagonal line of the pixel xy. Okay, because the diagonal line extends on, if you go down, it also goes to the right hand side. So that means, however, the number of steps we have to get down to the base is the number of pixels we have to move to the right hand side, and that's why we add y to x, to become the actual x coordinate of the base of the diagonal line. And because it is at the base, the y part, the y value is a 0. Once we figure out the g value at the base of the diagonal line, the next thing is to just add the value of y, because each pixel along the diagonal line as we go from lower right to upper left. Okay, for each pixel that we move in that direction, we are just adding 1 to the g value of those pixels. So the number of times we have to add 1 to get to the pixel at coordinate x, y is really just y compared to the g value at the base of that diagonal line. So now we expand this a little bit because we already know what this thing boils down to. It is x plus y times x plus y plus 1, the whole thing divided by 2 plus y, and that's it. This is the equation. Alright, so do we have any questions about the g function? It is now fully derived. So if you look at this equality here, that is how we define the g function. Okay, I'm not seeing any questions, which again is either a good thing or a bad thing, but I cannot tell when there's no information. Alright, so what we'll do is we're going to plug in this equation on values that we have already figured out by hand and see if it works or not, right? So we're going to say this is the x value, this is the y value, this is the g value of xy, and we'll go through a few examples. 0 seems to be a good one to check, right? 0, 0. Okay. In other words, at the origin of the entire two-dimensional space, what is the g value corresponding to that? Now, in the previous page, we worked out everything by hand, and we see, oh, it's just 0 because that's where we start. But we also want to make sure our equation would also give us a 0. X is a 0, y is a 0, x plus y is a 0. X is a 0, y is a 0, x plus y is a 0, plus 1 is a 1. But then we have 0 plus 1. We have 0 times 1, which is 0 divided by 2. That's also just 0, plus y, y is 0. 0 plus 0 is 0. Okay, that seems to work out. Let's figure out something that is a little bit out there. Okay, let's figure out the one that has a value of 8, which is this one over here. So the x value is 1, the y value is 2. Okay, so we have 1, 2 as the coordinate. So now we have to plug in, x being 1, y being 2 into this formula and see if we get 8 back. So x plus y is 3, x plus y plus 1 is 4. 3 times 4 is 12. 12 divided by 2 is 6. And then 6 plus 2 is indeed 8. Cool, that seems to work. That may be a fluke. Okay, let's check again. Okay, let's do something else. Let's pick another pixel and try again. So this time let's try, well, let's extend, let's make a new row. Okay, because somebody can say, but Tack, you just make it work because you got all of those values, figure out by hand. So we'll try another diagonal line. So this is 10, 11, 12, 13, and then we have a 14 here. So let's try this pixel over here. Okay, it is at location 2, 2. Alright, so at location 2, 2, we plug in the values again. 2 plus 2 is a 4. 2 plus 2 plus 1 is a 5. 4 times 5 is 20. 20 divided by 2 is 10. 10 plus 2 is 12. Woohoo! It works. So, are there any questions about how the g function is derived? I mean, I just went through a few steps to kind of verify that it's working for pixels with known g values, but we can kind of see that it kind of makes sense. Okay, the formula makes sense. But I want to make sure that everybody is understanding the material at this point. At least understand what g is doing. Alright, I'm not seeing any questions. Oh, cool. Angel is typing. You guys can use the voice channel to ask questions too. Maybe faster sometimes. All right. G is finding the natural value corresponding to a pixel. Yes, that is correct. All right. Any other questions? All right. So if there are no questions, the next, well, if you guys have no questions, I have a question. Because I don't want G to be just any function, I need G to be a bijective function. So bijection means, we are mapping two-dimensional coordinates to unique natural numbers. I think that part we can kind of agree, right? No two pixels is going to get the same value using this method of assigning values. Is that kind of obvious? Because we just keep sweeping with longer and longer diagonal lines, and the value that we are assigning to the pixels, just keep incrementing. So if you just think about this from the programming perspective, each pixel is going to get a unique value because we keep incrementing the counter. So there's no way for us to assign the same natural number to two different pixels. So that's kind of intuitively, quote unquote, proven. Okay, now that's oxymoron right there, because you cannot intuitively prove something. Intuition can guide you in a formal rigid proof, but intuition itself cannot be a part of the proof. It is just how you can move to the next step and the next step and the next step in a proof, but you cannot use intuition to substitute rigid mathematical steps in a proof. Okay, so that's one. We got injection. Now we need surjection. In other words, are we really sure that every single natural number corresponds to a pixel using this particular method? If I just give you a number, okay, since we have the tablet up, if I give you this number, all right, how do we know that this number does correspond to a pixel in two-dimensional space? Okay, I don't care how it is done. I don't care how you figure out, g of sum xy, equals to this particular natural number. I don't care how you figure out what is the x and what is the y. I'm just asking, how do we know there exists a pixel, xy, such that the g value of that pixel is this number? So is it intuitively understandable or not? It's sort of intuitive, right? Because we have a counter, right? Because we keep adding values, okay? Going from here and then here and then here and then here. So we are just keep sweeping, through the space, and that space is infinitely large, right? So when we are sweeping, we are also incrementing a counter, which means at some point the counter is going to be this value and will be at a particular pixel somewhere in the two-dimensional space, and as a result we know every natural number has a pixel corresponding to it. Now this is not a formal proof, it is really just an intuition kind of thing, but I think it kind of makes sense, right? Because as we sweep, our sweep using the diagonal lines from lower left corner and to the right hand side, eventually, okay, the counter would get to this particular value, and then whatever pixel we are at, by sweeping at that point, we'll get this value. So we know there has to be, a pixel corresponding to this particular value. Okay, so it is surjective. But now we have injective and surjective, right? Even though I did not mathematically prove that it is both injective and surjective, but intuitively we can understand that it is bijective. Cool. So if it is bijective, at this point we have already established a very, very important equality. So at this point, because we know this g, which goes from, okay, I need to, this g, which is going from the Cartesian product of natural number and natural number and mapping it to just the set of all natural numbers. This is our domain. This is our codomain. We know this G is bijective. And then based on something that we talked about earlier in today's lecture, that tells me one thing, okay? That tells me the cardinality of the Cartesian product between n and n is indeed the same as the cardinality of just the set of all natural numbers, which by definition is aleph null. Isn't that cool? Then what about the three-dimensional space? What about, so from here on, I'm just going to use a normal n, because it just takes extra time to write these funny n. So what about this domain? Okay, if I look at the cardinality of this domain, does it equal to this domain over here? Does it equal to the cardinality of natural numbers? That's the question. As it turns out, it has to be, right? Because you can apply G in a nested way. So let's say we're dealing with a pixel, a voxel this time, which is XYZ. It's called a voxel because a pixel is a picture element, which is a two-dimensional thing, and then a voxel means it is a volume element, and that's why it's called a voxel. Okay, so the voxel XYZ, if I want to map it to a natural number, I can just apply G twice. Now there are several ways to apply G. I'm just going to apply it in a, I guess the most natural way, which is grouping xy first, and then whatever G of xy is, I will pair that with Z so that I can apply G again. So by applying G in a nested way, I can now map a three-dimensional space to natural numbers. And because G itself, yes, Anita is correct. So it is indeed, I'm erasing the question mark because it is established. It is also just aleph null. What about four-dimensional space? What about five-dimensional space? They all have the same cardinality as the set of natural numbers. Isn't that cool? I mean, if you think about n Cartesian product to 20, so we're talking about the 20-dimension space, but when you look at the cardinality, it really is the same as just natural numbers. As long as this is an actual finite positive integer, we can establish the equality. That's interesting, okay? Because now we have a way to quote unquote fold any dimensional space into a single dimensional space. Now it only works for discrete dimensions, which means we cannot have 0.5 as a coordinate. We can only have 0, 1, 2, and so on. But nonetheless, it is still a pretty cool thing. So do we have any questions about this conclusion here? Okay, you can substitute the 20 with 100, 600 or whatever. Okay, it doesn't matter as long as it is just a finite integer value, non-negative finite integer value. It works. So, are there any questions at this point? Alright, doesn't look like we got any questions, and I'm just looking at the time. We got half an hour. We still have half an hour left, which is enough for the next portion, which is also a lot of fun. At least the derivation is. So let me go back and summarize just a little bit. This equation here, how G is spelled out using this formula over here, that I could not find on the internet. Okay, when I was doing the research, to teach this class, I think, oh, this is really a cool way. We have a way to assign natural numbers to pixels in a way so that we can establish the that n times n, has the same cardinality as n, and therefore it is, also known as Aleph null. So I just thought that is pretty cool, but can we figure out, a closed form equation so that we can actually, if I tell you the x and the y coordinates, we have a way to compute the value, the integer value corresponding to it, right? And the derivation to get to this point, that's all mine. That's all mine. Okay, I didn't copy this from anywhere on the internet. So now we know that g is bijective. So one thing that we learned about bijective function on Monday is if a function is bijective, there's an inverse function. Okay, so this means there's an inverse function, g, superscript minus, so that it maps from n back to n times n, right? Because all we need to do, the inverse function will just kind of flip the domain versus the codomain. So what used to be the domain for g is now the codomain of g inverse. What used to be the codomain of g is now the domain of g inverse, right? So the problem, it's basically this. Okay, if I apply g, the inverse of g to a gigantic value, okay, let's pick up the one that we were working on earlier. Let's pick up this one here. Okay, so let me select it. And then paste it over here. Copy the clipboard, tap any page with marker. Okay, there we go. Click it. And then move it around until it is here. And change back to my pen tool. Alright. So now, I want to figure out which pixel give us that particular natural number. Okay, so that's the job of G inverse. You give it a single natural number, it will find out which pixel will be assigned that particular natural number. Alright, so conceptually, this is not difficult to do, right? You just have to use that, your sweeping motion. Okay, let me go back to a picture where there's a sweeping motion. So all you have to do is to start with this. It's 0. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And all you have to do is to keep going until you get to 12,476,613. Then you will find the exact pixel that will be assigned that natural number. It's doable, right? It's doable by, once again, using a double loop structure. You can do it. But do you want to do it that way? The answer is, well, if we don't have a choice, I suppose we can do it that way using a double loop. But since there's a better way to do this, we'll go ahead and use a better way to do this. Alright, so now we're trying to find the closed form of G inverse. So when we look at the closed form of G inverse, when we try to derive that, we are basically looking at a inequality, and we basically start with the base again. Okay, so that reasoning is all contained here. And the reason why I throw in all these proofs and also why how I proceed with all the steps within the proofs is I want to show you how, at least how my mind works when I need to prove something. That may or may not be handy to you, because I think most of you still probably have some more math classes to take. I can be wrong. But computer science as a field is really a subfield of mathematics. So the line of reasoning is actually quite important. You may not be doing this kind of algebra again. You may not be even touching, formal mathematical proof again. But every time you debug a program, you are applying logic. You are basically using the same techniques as a mathematical proof when you're trying to figure out why the program is not working. It just doesn't look like it. Okay, it just doesn't look like it. It's kind of like, when you look at a um, when you look at a professional, fighter. Okay, um, I guess MMA is one of those, organizations where they have matches. Okay, so but those people practice, various forms of martial art, and but when you see them fight, you don't quite, you cannot quite tell. Okay, oh, this is, from, the Shaolin technique, and this one is from Thai boxing technique, and so on. They just utilize those techniques, whenever it is applicable, right? So it's the same thing here. Okay, when you are learning how to prove and you have all of those techniques in your mind, they do not seem to be directly applicable. They seem to be like, it's kind of like learning Tai Chi. Okay, you say, these people they're moving so slowly, they cannot catch anything. I mean, they cannot use it for defense, and they cannot. It's not practical. But the motion is, there's a reason why they move in a certain way, and if you accelerate, those motions, they are actually effective. Okay, to a certain extent, in an application of, you're in on the stage fighting. So it's the same thing. Okay, when you are proving theorems in a math class or in this class, you are exercising, a way of thinking, a way of reasoning out something, logically and very rigidly. And that technique one day can be applied when you're debugging a program. Okay, so that's all I'm gonna say about this topic, because I know some people will ask, but why do we have to read through all these proofs? Why do I have to learn math and so on and so forth? It's because, debugging a program involves the same kind of logical thinking. All right, so now
Professor, I have a question
yeah, yeah,
for
go
you.
ahead. Absolutely, go ahead.
Okay, so as we're covering this material,
Uh huh.
one of the things that I am thinking of is if we came up with a closed form equation,
Mm-hmm.
that would reduce the time complexity of our equations to like
Constant time.
like a
Yep.
right. So if we master this like these skills that you're teaching us
Mm-hmm.
when we are writing, instead of going through like loops like you're suggesting,
Mm-hmm.
which will increase our time complexity,
Mm-hmm.
this is a way to decrease our time complexity as we compose those functions, correct?
That is 100% correct, and which is a very pragmatic reason why we want to be able to go through these derivations.
Thank you.
Very good. Thank you. Thank you. All right. So now getting on to, what we need to actually resolve, right? So we are given a gigantic value, which is, I'm just going to call it n over here. We want to find out where the pixel is. Okay, so that's kind of going like, this is kind of difficult. Well, it is kind of difficult, but at the same time, there are things we can do to help us with this. Okay, so what we do is we say this is given, n is given. We are try to figure out x and y. Okay, so the value is given. Where it is we're trying to figure that out. Okay, but we know something about the base of this diagonal line. Okay, so if you extend this, diagonally, we know that at some point it's going to hit the bottom of. Oh, you guys cannot see the screen. Let me. Oh, there we go. So if we are given n as a value and we want to find out where that pixel is, okay, then one thing we can do is to extend the diagonal line all the way to the base, and we know at the base the coordinate is going to be x plus y 0. That is the coordinate of the base of that diagonal line. So with x plus y, okay, instead of writing x plus y all over the place, we are defining a new variable called w, which is just by definition x plus y. Just so that I don't have to write x plus y over and over and over again. Okay, it's just laziness on my part. So w is defined to be x plus y. So the value corresponding to this thing is pretty easy to figure out. I mean, at least we know, what it looks like, right? So we know this pixel has a g value of so g of x plus y 0 is going to be w times w plus 1, the whole thing divided by 2, right? This is from an earlier derivation. Yes, we don't know what a w is, but we know this value is relatively close to the value that we're given, which is n. Because what is off from those two is n is w times w plus 1 divided by 2 plus whatever the y is. Okay, we need to figure out what the y is. We need to figure out what is w. But there are some relationships between those things, and we can figure out the relationship. So we know this is the relationship, and w really is just x plus y. Okay. All right. Well, that is kind of cool. But how do we solve this whole thing? Because we know what n is. This is given. We don't know what w is. Okay, so w is unknown, and w is unknown partially because y is also unknown. So this is also unknown. So when you look at this, it would appear that we have two unknown and only one equation, and there's no way to solve this. It looks that way, right? Well, it's not quite that way, because what we know is w is partially dependent on y. That's one thing we know. But we can also do something like this. Okay, we can just kind of get rid of the plus y over here. Then you go like, but then it's not an equality. You're right. It is now a inequality. So now we have n being greater than or equal to w times w plus 1, the whole thing divided by 2. Ah, man, it is now it's worse. Before we had the equality, which means when we solve it, we actually solve it, right? Now it is an inequality, which means how do we solve an inequality? Well, let's kind of work this out a little bit. Okay, so we'll go ahead and expand the two sides. So on one side we'll have w squared divided by 2 because of that, plus what? Plus 1w divided by 2, and then plus 1 half. Okay, I'm just expanding the whole thing. Okay, so when you group all the constants, okay, so now we have 0 is greater than or equal to. Let me change the way it looks, okay, because then you guys will go like, oh, so this is something that we know. Okay. And then this one is 1 half minus n. There we go. So other than the inequality, what do we recognize here? In other words, I can't really just cover up something, but if I'm just going to move one of the windows on my screen here. So I'm just going to cover up the 0 is greater than or equal to. If we just look at this part here, what does that look like? N is given, okay? N is a known value. What does it look like? A quadratic. Very good. So this is a quadratic inequality. All right. So how do you solve a quadratic inequality? You solve it as if it is an equality, and then you just say, but by the way, there's a whole bunch of values of w that can make the inequality happen. There are only two w values that can make the equality happen, but when I change the equality to an inequality, then there's a whole bunch of w values that can meet the requirement. Okay, so are we doing okay so far with this math thing? I hope so. All right. Well, assuming we're good. So assuming we're good, we go through the derivation. So, over here, I just multiply everything by 2, because if you multiply 0 by 2, you still get 0. And then the other side just looks nicer. Okay, that's the only reason why I multiply both sides by 2, is so that we don't have halves and 0.5s to deal with. Okay, So now we know how to solve a quadratic equation, right? Now I have to be honest, okay? I cannot remember, how to solve a quadratic equation. I had to look it up, okay? Um, but in the end, we have two roots, right? Because this is a plus or minus, so we got two roots. One of the roots we can toss away right away, okay? The root where w is negative, we can just toss it away because we know x is a natural number, we know y is a natural number, and w is the sum of two natural numbers. So it has to be greater than or equal to 0. So that means anything that's negative, we can just toss it. So that means we only got one root left, which is the positive root or the non-negative root. So the non-negative root is going to look like this, okay, without the floor symbol applied to it. The floor symbol is applied because we know w is a natural number. So if w is a natural number, the root itself can be a irrational number. So that means we have to apply the floor operation so that we can maintain the less than or equal to 0 relationship, but at the same time satisfy the requirement that w needs to be a natural number. So that's why we have to apply the floor operation. But the bottom line is we can now solve for w. Okay, it looks kind of messy. It has a square root in it, but if you tell me what n is, I can just say, oh, okay, just go ahead and compute the square root of 8n plus 1. Take that square root, subtract 1 from it, and then divide the whole thing by 2. And then we take the floor of that number. That becomes w. Alright, so we can solve for w now. Alright, so if we can solve for w, how is this going to help us, right? So let's go back to the tablet and then we'll take a look at the picture. So what we can do now is to figure out, we know how to solve for x plus y given n. So we know where the base of the diagonal line is. And we know the value, we know the g value corresponding to the base of that diagonal line, which is right here. So now the question is, but how is that going to help us, right? Well, it's going to help us tremendously. Because if you think about, what is n and what is the g value of x plus y 0. Oh, let me fix this. What is x plus y comma 0? That is y. Because the value here is given, it is n. The value over here is g of x plus y comma 0. So, and the difference between these two values has got to be how much they are off vertically, which is y. Is that okay? So we can solve for y now. Okay, once we solve for w, we can then solve for y, and once we get y, x is also easy because x is going to be w minus y. So now we can solve for both x and y, which is kind of what the notes is saying. The notes is a little bit dry without the pictures, but with the pictures, it is a little bit easier to understand. So in the end, okay, when we are all done with all these derivation, so instead of using w as a as a variable, w becomes a function. So w of, if you give me n, which is the natural number of a particular pixel, w as a function is really just applying the root of the quadratic equation. And once we figure out w, we can now figure out y. And once we figure out y, we can figure out x. So in the end, the inverse function of g, the g inverse, if you give me a natural number, is really just boiling down to this. Okay, we have to use w because it's an ugly function, but we only have to compute it once. Even though it appears like 4 times, you only have to compute it once. You just reuse the same value over and over again. So w of n times w of n plus 3, the whole thing divided by 2 minus n, is going to be the x value of the pixel corresponding to the natural number n. And then n minus w of n times w of n plus 1, the whole thing divided by 2, is going to be the y coordinate. And that's it. Okay, so the only thing that is slightly time consuming is square root. With any modern processor, especially a desktop processor, there's a floating point unit, and so square root itself is really not that time consuming to compute. Well, if anything, it is a constant time computation as opposed to scanning the diagonal lines. That is a big O of n. Okay, the larger the value, the longer it's going to take. But square root takes the same amount of time. It doesn't matter what gigantic n value you want to specify, it's going to take the same amount of time. So once again, Angel is correct. Quick math makes it, simpler. Well, it makes it doable, okay? Because if I give you like some gigantic value, you can just apply it here, and then you get the x and the y value. All right. So, do we have any questions? Because we still have like 7 minutes left. Any questions? Oh, we got questions coming. Nice. I like that. Oh, you mean the homework assignment? Yeah. Let's go ahead and do that. Okay. I do have to apologize because I thought I fixed the questions, and apparently I did not fix them all. And so, some of them look kind of icky, and that's why I had to send the announcement. And even that doesn't fix everything, unfortunately. So I'm gonna have to go in and manually grade, these questions, because of the way they are not rendered correctly. So we'll go ahead and take a look. Okay, so question number 4. So we'll skip to question number 4. There we go. Alright, so this is question number 4. This x2 is not supposed to be x2. It is supposed to be an actual value. But since it appears as x2 for everybody, and x2 is not in the domain, we basically have to say f is not even a function, so a 0 would work. Sure. Let's do one of the other ones here, which is not formatted incorrectly for the class. Sure. So let's go look at question number 1. Question number 1 looks okay, right? I mean, no missing parentheses, no x2. Okay, so we'll work on this one. Alright, so we have the domain as x, okay, because, we want to see if it is a function where x is the domain and y is the codomain. So we look at this, and we see that 1 as a value of x does not appear as the first item of any tuples in f. So f is not a function, so we put a 0 here. Because if it's not a function, you don't even bother to say whether it's injective or surjective. It simply does not apply to non-functions. Alright, so let's move on to the next one. Alright, this one also looks good. Okay, so this one is a function because we can see that 0, 1, 2, they all appear once and only once as the first item of a 2 tuple in f, so that's good. So that means we have at least 1, okay? And now we want to see whether it is injective, which means are they all mapping to unique values in the codomain, and they're not unique because we can see 0 maps to 1, 2 also maps to 1, so it is not injective. And we want to see if it is surjective, and we can definitely see it's not surjective. There's no way it can be surjective because x has fewer elements than y. That is why it cannot possibly be surjective. So that means the answer to this one should be a 1. Moving on to the next one. Oh, we got some questions. Okay, so let's wait for Jonathan to finish typing, or Jack to finish typing. Alright, so for functions with the same cardinality as the range. Okay, I see what the question is. Okay, so the question should read, for functions where the domain has the same cardinality as the range, which is the codomain, Is it even possible for that function to be injective but not surjective? The answer is no. Okay, so if a function has the same cardinality for its domain and its codomain, if it is injective, then it has to be surjective as well. So that's a good point, good observation there. All right, so moving on to this one. And of course, that observation is not exactly a proof. So now, we can kind of think about how to prove theorems like this, right? So the theorem, okay, this is kind of on the side. If you want to work on a proof like this, or at least think about how to prove it, this is a ungraded assignment. Okay, you can kind of treat it that way. So the ungraded assignment is, okay, I will type it in the text channel, for a function f where x is the domain and y is the codomain. If x and y have the same cardinality, I think I typed it correctly, and f is known to be injective, then oh, okay, that's not what I want to do. Then injective if and only if surjective. There we go. Alright, so if you look at the text channel, that's kind of the problem, or the statement that I want you to think about how to prove. Okay, for a function where function f where x is the domain and y is the codomain, if x and y have the same cardinality, then injective if and only if surjective, not subjective. Let me change that. Surjective, not subjective. In other words, if you have it injective, it has to be surjective too, but if it is not injective, it cannot be surjective. So kind of think about how to prove this. But getting back to the assignment over here, so this one has the same situation, where 2 is being mapped to twice, but it is a function. So we basically say just 1 in this case. And then this one is a problem because it shows a x2 here. So I'm gonna have to grade this one manually because I'm pretty sure it has a non-zero answer, or intended answer is non-zero. Alright, so we get to this one. 0, 1, 2. Oh, this one is exactly the same as the one before, so it's just 1 because it is not injective, and because the cardinality of the domain and the codomain are the same. If it is not injective, it cannot possibly be surjective. And then we have the I'm missing a few questions, or it thinks I'm missing a few questions, because an answer of 0 unfortunately is it'll give me a false positive warning when I submit it. You guys will see it. Alright, so this one it is a function, it is not injective, and it cannot possibly be surjective. So this is also just a 1. Alright, so let's go back and check on the earlier questions. That is a 0. And then question number 4 is also a 0. Alright, so submit quiz. And it's giving me a false positive, as a warning, because I did answer all of them. It just did not register a 0 as a correct as an answer. So now when I look at the graded version, okay, 1 of 1, 1 of 1, 1 of 1. Oh, this one is also 1 of 1. 1 of 1, 1 of 1. So I got them all. Cool. Alright, so we are running out of time. In fact, we have run out of time by 2 minutes already. So you guys have a good weekend, but over the long weekend, please review the material, and we are gonna move on to the next module next week. Okay, so let me show you what the next module is. It really is just kind of sequentially down on the list. So we are now done with Aleph No, and hmm, so I'm not sure whether we can. It's time for exam one yet. Okay, so I think we're not gonna do exam one just yet. Exam one is gonna be in week 6. We are not in week 6 right now. We are probably in week 4-ish. So we got 2 more weeks to go. So the next topic that we're gonna talk about is relations. Taking row. Ooh, yes. Let's take row today. And the word to take the word for row taking is okay. I'll use sigma. There we go. So I'm gonna do it right now. You guys can just hold on a little bit longer when I'm doing this. So we'll go ahead and make a quote-unquote quiz, which is not really a quiz, and it is for row taking purposes. There we go. And then we edit. I'll give you guys until 2 p.m. to turn it in. That should be plenty of time. Today is the 10th. Alright. And then go to the questions. Add a question. And then this is going to be fill in the blank. And the word is sigma. S-I-G-M-A. And I'll take uppercase S, sigma. So both will be considered correct. Update question. And then save and publish. There we go. Alright, so if you refresh your browser, you should be able to take row, for you can indicate you're present using the row taking activity for today, and the word is once again sigma, S-I-G-M-A. Alright, Tom is typing, so I'm gonna wait a little bit. Or not. Alright, so I think we're good for today. So I'm gonna turn off screen share on Discord and also on YouTube, but I will continue to stay online for maybe another 10 minutes just in case people have any questions. Yeah, go ahead, Garrett.